One useful rule connected with equilibrium is if an object's center of mass moves outside of its base of support, it will tip over. This is for things that are sitting on the ground, not things that are anchored to something. But if you think about it, this is a reason why we put training wheels on bikes for small children. When you're just starting out, you can't pedal very quickly. You're starting out at a very low speed, and at low speeds, it's hard for even adults to balance a bike. And the reason is you're trying to keep your center of mass positioned to within half the width of the tire, which is, a centimeter or two. The child will very easily get their center of mass off the center of the tires and tip over. So if you put the training wheels there, that gives you a much larger base of support and makes it much less likely that the child can tip over. You see the same thing on bucket trucks and cranes. These things are called outriggers, the little legs that stick out from the base of the crane or the truck to make it less likely that it will tip over. If we want to find the angle where something will tip, let's say we've got a snack machine, for example, that is 2 meters tall and 1 meter deep. How far can we push it before it tips over? We assume uniform density, which of course it's not going to be in any realistic machine, but this is just to make life easier. That puts its center of mass at its geometric center. And then what we would imagine doing is tilting until the center of mass is over the corner. If you notice, once you're at this point, you have a right angle between this line connecting the center of mass to the corner and the floor. So we have theta here for the angle that it's tipped, and this angle must be 90 minus theta. However, we can also see that that angle, 90 minus theta, that's connected to this angle. If we call this theta, where we look at the angle between this line going diagonally through the block and the line that represents the vertical edge of the block, that could be theta. That will also be connected to this theta, the tipping angle. So we can just look at the geometry of the object in this case and figure out what the tipping angle is. And what we would see is theta is the arctangent of half the width divided by half the height. In this case, that's about 26.6 degrees. If we push it until theta is larger than 26.6 degrees, it'll tip over and land on the long side. What angle do we have? How far do we have to lift it up to get it to stand back up? And in that case, we will be doing the same thing, only now arctangent of the inverse of what we had before, and that's 90 minus 26.6 or 63.4 degrees. This seems like a pretty useless fact until you realize if you've ever had to move something with a hand truck, that's what your muscles will figure out automatically. You'll find that tipping angle, because if the angle is too small, the hand truck will tend to stand back up and bring you to a stop, and if it's too low, you run the risk of it falling on you. Now, keep in mind, if you try this with a snack machine, things are not in general uniform density, so you can't assume you have that kind of angle that you can tilt it before you run the risk of getting crushed. There's another standard problem you always see in an equilibrium chapter, and that is, let's say we have an 80 kilogram person climbing a 5 meter long ladder that's 20 kilograms itself. The base of the ladder is 3 meters from the wall. There's no friction between the top of the ladder and the wall, and the person is 1/3 of the way up the ladder and it's about to slip. What's the coefficient of static friction between the bottom of the ladder and the ground? We first draw the free body diagram, and we realize there's a vertical normal force and there's a horizontal normal force from the wall. The presence of that horizontal normal force is the reason why you wouldn't put the ladder up against a window. The frictional force, we'll find that in a second. It's Fs max. It has to point towards the wall. We don't have a frictional force up here. This is not really a bad approximation because you don't generally want there to be a large frictional force between the top of the ladder and the wall, or else you could pull the paint off the boards if it's a painted wooden house. We have the mass of the person times g, the mass of the ladder times g, and we can also figure out if it's a 5 meter long ladder and the base is 3 meters from the wall, the top must be 4 meters from the ground. We have a 3, 4, 5 triangle. So, having all these forces in place, we can now figure out what this coefficient of static friction is. So we have our usual equations that we can pretty much always write down, But in this special case, even though it's about to slip, it hasn't yet started slipping, so the accelerations are all 0. And then we say, what do we have in the x direction? We have Fs max pointing to the right. We know it's Fs max because it's about to slip. And we have NH, the horizontal normal force from the wall, pointing to the left. Those two forces have to be equal since there are no others involved in the x direction. In the y direction, we have the vertical normal force, and then we have the two weights of the ladder. The weights of the ladder and the person. So we can find this very quickly, 980 newtons, the total weight of the person plus the ladder. We also know that since the force of friction is Fs max, we can write that as being equal to µs times nv. So we see that our µs, which is what we're looking for, is nh divided by nv, and we already know nv, so it looks like we're almost done. The last equation we have is torque. We pick the bottom of the ladder as our axis of rotation. The reason is we get rid of two forces which could otherwise give us torques, the vertical normal force and the frictional force. So we use clockwise torques, we call them positive, and the various torques we have, torque due to the person, they are 1/3 of the way along the ladder, that's the distance, mpg, that's their weight, and then sine of the angle between them, theta, that's the angle between the ladder and the vertical, since mpg points vertically downward and the ladder is in the direction of r. So this is the top angle in this triangle we have here. We could say this is our theta, that's still theta, that's theta, all these things are theta. We can find theta since we know that the distance from the bottom and the top of the ladder to the floor and the wall, we get 36.9 degrees. So we could calculate the torque delivered by the person is 785 meter newtons, and it's positive. The ladder's torque will also be positive for the same reason as the person's, it's counterclockwise. Now we have 1/2 times the length of the ladder, which is 5 meters, times mass of the ladder times g times the sine of the angle. We get 294 meter newtons. Then finally the torque from the wall's normal force. It's at the full length of the ladder, 5 meters away, nh, and this is 90 minus theta, the angle here. So where we've had theta for these other cases, this time our angle is 90 minus theta. And that means what we get out of this, if we do sine of 90 minus theta times 5, we'll get 4. So we can now find this nh. If we plug this thing in, we get nh is 270 newtons. There's an easier way to do this torque problem, though, and that's the idea of the lever arm. The only thing that matters in this torque equation for the length of the lever is the length of the lever perpendicular to the force. That's what sine theta gives us. So the ladder's length times sine theta is 3 meters, which is the horizontal part of its extension. This means what we could do, if we take the ladder's length times sine of 90 minus theta, we get 4 meters. That's the vertical part. So we could write the torque due to the person as 1/3 times 3 meters times mg, and we get 784 meter newtons, which is the exactly correct answer. For the ladder, we get 1/2 times 3 meters times 20 times 9.8, which is 294. And finally, from the wall, we would get 4 meters times nh, and this one is negative. We can solve for this, and our real answer for nh is 269.5 newtons. So this gives us a µs of 0.275, fairly